Yes. So today I'm going to talk about our unique technology, which is called a dynamic pixel tuning, and that is for the micro displays as well as either it can be used for automotive application or as well as the smaller size of the display, both of the applications. So basically, I will talk a little bit about our company, then their technology and what we are going to do, what is our plans. So let me introduce our company. We are a very young company. We just spin out from the Cambridge University in 2020. And most of us are having a lots of R&D experience for more than 15 years in GAN field. And we are having a good patent portfolio, which is nearly around more than 70 patents around this GAN technology. And we also produced our first in-GAN red, which was in November 2020. And then we aggressively tried to do the same micro displays on and produce all the three colors with the brightness of the nearly around 2 million nits, max brightness of the 2 million nits in the green color in November 2021. And then we came up with a new approach, which is a single pixel. We call it DPT, which single pixel can produce all types of color, and which we demonstrated in the SID conference display week in 2022, and we won the best prototype award there. And we also moved towards 200 millimeter, and now we are moving towards 300 millimeter, and we are expecting it to come with a 300 millimeter LED approach on 2023. And then finally, we are doing some kind of working with our display partners as well as the backplane partners to utilize the DPT technology completely on a product label. And the direct advantage of the dynamic pixel tuning is that where people have to work on sub-pixel concept, where they have to do red, green, blue, that type of LED sub-pixels, we can do a larger emitter size and with keeping the same resolution, or at the same time, we can increase the pixel density, keeping the same chip size. So in that case, we can have the larger pixel density, we can have improved brightness, and as well as where people have to work on three different material systems, we can work on the single material system, which can enable us to consume less power, as well as it can extensively reduce the cost, because when people are talking about the mass transfer, this type of technology with the smaller pixel, where again the pixel size is limited, where we cannot go beyond 10 micrometer pixel size, we can do everything on the larger pixel size. We don't need to do the mass transfer. We can directly do a wafer to wafer bonding, because one LED wafer, one type of CMOS driver or any type of TFT, we can just directly bond it on a single substrate. So that enables and that solves lots of manufacturability problem, as well as enhance the performance, overall performance. And as well as just now William was talking about AU, that the transparent displays, they are suffering because they are looking for a very good high efficiency emitters with a small pixel size. This type of solution can be a promising in that type of application. So, and the second thing is that all of them are where people are talking about the mass transfer, working on three different material systems. They have to do three different steps of the mass transfer, and they have to do the binning and this type of thing, which requires a lot of additional step and additional cost. And we don't need to do that. We just need a single emitter, single wafer of the LEDs, which can emit all type of colors, and we just do the wafer to wafer bonding. As well as this, all these things are on in-GaN material. And we know that L-in-gap or gallium arsenide, that type of things are more prone when there's a size dependency is coming, and in-GaN material are less prone in terms of the size dependency. So our solutions are all on in-GaN, so that even for the smaller size, we have a higher efficiency of the emitters. And like we say, in terms of the manufacturability, first you have to deal with all the blue materials, do the mass transfer or pick and place, whatever we do, and then the chip bonding, and then whatever integration we have to do on the backplane from the driving part. So 3 design needed for R, G, and B. And for the green also, then we have to deal with a separate material system, which is L-in-gap or gallium arsenide red material, and then we have to do the same mass transfer process, 3-time mass transfer process. If we assume that each time mass transfer process is 70% yield or 80% yield, then 3-time it is going to be less than, say, 25% yield, and that is resulting in the higher cost of the products, and that is very difficult to get into the market for the consumer products. So when we are talking about the small pixel size less than 10 micrometer or even 20 micrometer, people are struggling with the yield loss, and this can reduce a yield loss by 3 times, because we only need to do the things on one single step, which is like this, where we will just choose one DPT material, one chip manufacturing like a LED, single LED, and then single air singulation. Either we can do the pick and place, mass transfer, or wafer to wafer bonding, this type of things which improve the yields significantly. And then we choose the integration on the back plane, and then this whole things can do on a single material system, single design, which can effectively reduce the cost and the power consumption by 80%. And this all are applicable to all type of direct view, as well as the HUD type of the markets, or tablets, or wearables, as well as the micro displays for the AR VR applications. So if we talk about the transparent display, we just use our micro LEDs, and we just use some off-cell backplane and just a smaller emitter size, and then we try to do some kind of transparent displays on the available, means we didn't do any kind of backplane, we just take it off-cell backplanes, and which is nearly 40 ppi, not a very good in terms of the ppi. And then we demonstrated that what type of displays we can do in terms of our material system, where we put our red, green, blue and material together, and then you can see that we can achieve a quite good color combination as well as the color gamut. And in terms of the DPT, we also did several prototypes where we demonstrated that how we are going to achieve all the colors from a single material system, from a single LED. So if you see in this, these all are based on the DPT concept, where we are showing that how we are going to do the color mixing, and it is on a single LED. So chip level, we can produce different type of colors, just from red to blue, as well as on the active matrix. Also, we show these active matrix backplane was on the LCOS backplane, just off-self backplane, means there is no special design we have done for that demonstration. And then you can see that each frame, from the frame wise, we can achieve from blue to red all type of colors from a single backplane. So overall, this DPT concept is going to reduce the complexity of the whole micro display. Either it is for the automotive application, or either it is for the AR VR application, or either even it is for the wearable or TV signage, that type of application, because you have to deal only single material system. And you can even do the larger emitter size if you want a higher efficiency, or higher luminance, because the emitter size is important in terms of the enhancing the luminance. As well as if you want a higher transparency, you can reduce the size, because you don't need to deal with the 3 subpixel system. You can do or you can use 1 subpixel, and then other 2 subpixels are just empty, so it can be a blank. So it is direct impact that how the transparency is going to improve. And the only transparency will be affected by the metal lines, not by the micro LEDs. And if we are talking about the metal lines, you have to deal only one single LED metal lines. You don't need to do red, green, blue metal lines. So most of the part of the display can be completely empty. So that can directly impact the transparency which people are trying to solve. And I think if AUO have demonstrated something which is 60% transparency, if this type of technology where they can reduce the metal line by third, then it is very easily achievable by that transparency can go beyond 80-85%. So this is all about how the DPT is going to impact the micro display, as well as the all type of display manufacturing, as well as the performance wise. So this is what actually is my talk, to just demonstrate what actually DPT is, what is its functionality, and how it's going to affect the whole market.
Thanks a lot, Kunal, for this really interesting presentation. And we have already two questions. Benjamin, please, you can start from Forvia.
So I have two questions. So basically, what is your status right now in terms prototype, mass production, and things like that? Second question, reliability. What kind of tests did you perform with this new kind of LED type?
Okay, so your first question, our status is that we are at the prototyping stage because we are working with our backplane partners who is trying to do some kind of backplane which can enable us to actually not doing it frame by frame, means actual active matrix. So once that type of backplane is available, we can easily demonstrate the full color solution. So that is what is the prototyping stage. And in terms of the reliability, we have done some kind of reliability so that how this is not going to change in terms of the color gamut curve. So we have done a very stressed test for more than 500 hours, and the curves remain same. So, and I think that is, and we are also doing the normal LED like 85, this type of reliability test, but that is more like a similar thing which will be happening for all the LEDs. This will be also the same impact because we are not doing any special design, or we are not doing any kind of stacking, or we are not doing any kind of horizontal stacking or the vertical stacking. It is just a single LED, single set of the quantum well. So it is just a single LED. So what LED is having the problem or advantage, this LED will be having the same advantage. So in terms of the reliability, we already confirmed that the slope or the curve which need to obtain for the color gamut all will remain same for 500 hours, and other part are less of our concern in because it is just a single LED.
Okay, thank you.
Thank you, Benjamin. And yes, please, Stefan Ludgen from Meta, please ask your question.
Yeah, thank you very much for the interesting talk here. My question is, in view of efficiency of red, where you may limited with the performance, and is it in-galp red or is it in-gun red? Maybe I guess these are still the limiting factors. And when we see your DPT panels, this is pretty dim. Yeah. So the question is, how can you overcome this problem in view of efficiency, or do you have any wall plug efficiency or any EQE data for red, which is the limiting here, I guess?
So, okay. So I will talk in two different perspectives. The first, we have in-GaN red, means which is stable in-GaN red, and we are approaching in-GaN red with a 30 micron pixel size. We have measured our efficiency is nearly around double digit, that is nearly around 10%. So 30 micron pixel in-GaN red is nearly around 10%, which we are targeting next year to improve by 15%. So that is for the single color. Now we come to the DPT one, and in terms of the DPT one, our if I explain in correct way, the DPT is less concerned of EQE numbers because for the EQE for the driving part, we need to put the current density to achieve the different colors. So in terms of that, if you think we need a low current density to achieve red and higher current density to achieve blue, as well as in terms of compensating the brightness, we are playing with the duty cycle, where blue need to have a smaller duty cycle, which is operating at the higher current density, which is a good thing for us because that can reduce the power. And in terms of the red color, where we are going to consume max of the duty cycle, which will be nearly around 95 to 97% of the duty cycle, which is operating at the low current density. So our approach to keep improving is that that particular slope of the current density, where we are achieving from red to blue, we are trying to inject more current density in red and reduce the current density in terms of in blue. So that will compensate the brightness. So that will be our approach and the solution.
Or maybe another matrix here. So you mentioned the performance of the I don't know if it was EQE or wall plug efficiency. from 10% to 20%. What is the
EQE number?
That was the EQE number, okay. And but that was for a pretty large micro LED, which is fine for the automotive application. Yeah, is the DPT, the power consumption, something where you said this is a big advantage? What would be roughly the power consumption or the wall plug efficiency of the DPT display then?
If we talk about the power consumption and considering the duty cycle, we have calculated for the micro displays for pixel size of 3.5 micron and the display active area is nearly around 0.26. In our calculation, it is nearly around at the moment it is nearly around going to be 0.5 watt.
0.5 watt. Okay. 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 Thank you.
Thank you.
That is because of the limitation of available backplane. Once we have the backplane, proper backplane, then this is significantly going to be reduced.
Okay. Okay.
Thank you, Stefan, for your question. Yes, we have two more questions. Please, Christian, if you can make it short, and please also, Kunal, a short answer.
You mean me? Okay, Christian van der Sluis here from Porotech. I was trying to find out when Porotech is ready for a prototype with clients, and in what format.
Yeah, we are for the full prototype. We are working with our backplane partners, and we hope it to be next year, in some way around next year, early next year or the mid of the next year. We will be coming up with this solution on the full color panel.
Oh, thank you.
Thank you, Christian. And yes, last question from Giovanni Cotella. Huawei, please.
Hi, thank you for the presentation. Just a quick one on the color purity of this dynamic DPT, and also like in the demo I saw at SID and this year on the top left, I see that there is no blue in that demo. I was wondering whether there is an issue there, or like I mean, why you decided not to have the blue pixel in the demo, and yeah.
Okay, the thing was that if you see the left side of the demo, that was on PCB, and the PCB, the ICs which we choose to drive it was not having that large range of current density. So that's why we were not able to achieve to the blue. But at the same time, if you see the demonstration in chip level, we are achieving all the colors, which is the right side of the top right side.
Okay. And the color purity of this mode is sufficient? I mean, which color gamut you can achieve?
Currently, in terms of the volume, color volume, we are able to achieve DCI.
Okay. Okay, I see. Thank you.
Thank you, Giovanni. And thank you again, Kunal, for this really interesting presentation. It raised a lot of interest. Thanks a lot.
Thank you.